Hey, AP Chemsters, this is Mrs. Mandalay bringing you another edition of the Blank Wall. This is our opening for Chapter 18. It starts off with balancing redox reactions. This is a review from what we've already done from earlier. I think it was Chapter 4. We went into these rules. So 18.2 is just a review. We've done this. So I'm going to go kind of quickly and hopefully that you recall us doing some of this. So it says rules for balancing. This is the order in which I would do them. It says assign oxidation numbers to all atoms and identify what's being oxidized and what is being reduced. You might recall how we went about doing that. You're looking at some rules where you saw all monatomic elements have the charge as their oxidation number. All just elements that are atoms are 0. Oxygen will be -2 unless it's a peroxide. Fluorine is always -1, and then salt for all the others. Okay. It says write separate reduction oxidation reactions. Reduction, the numbers go down. That's why they call it reduction. Oxidation, the oxidation numbers go up. For each half reaction, you need to balance the elements, save oxygen and hydrogen for later. You balance oxygen using water, balance hydrogens using H+, and balance the charge by using electrons. You might have to multiply both sides by some number so you gain and lose the exact number of electrons. Add them, and then if it's in base, add hydroxide for every H+. This should bring back memories. I'm not sure they're so fond memories, but we have done this. So what's the first thing I do is assign oxidation numbers to everything. Well, right now I can see the oxidation number of iron is +2, and this iron is +3. So what just happened here? The number went up, so that's my oxidation. So let's do this. Fe2 plus goes to Fe3 plus. Okay, so I just wrote down the half reaction, just did that first one. Balance the elements. I have 1 iron on each side done. Do I have any oxygens? No. Do I have any hydrogens? No. So what's the only thing left to do is to balance the electrons. Here I have a charge of +2. Here I have a charge of +3. My more positive side will need the electrons. So my iron +3 has more positives, so I'm going to add 1 electron to balance it out. So that's my oxidation. My reduction is going to be my manganese. Okay. Well, I didn't assign it an oxidation number, so let me go up here. Manganese, as you know, is a transition metal. It's not an always, is it? So how do I figure out the oxidation number of manganese here? I'm going to use that equation. So 1 manganese plus 4 times -2, that will always be the oxidation number of oxygen in a compound, unless it's a peroxide, is equal to its charge. So Mn minus 8 equals -1, Mn equals +7. So that's the oxidation number of manganese. So this is +7, and the ion right here is +2. So obviously I did find the right one. It is being reduced from +7 to +2. So now what do I need to do? Let me scroll down a little bit. So I need to balance the manganeses. I got 1 on each side. That's good. Now balance the oxygens using water. If I have 4 oxygens on the reactant side, I'm going to add 4 waters on the product side. And now balance the hydrogens using H+. Well, I have 8 hydrogens here, so I'm going to have 8 H pluses here. So now what do I need to do is I need to figure out what's my overall charge and then add electrons. So my reactant side, I have 8 pluses and 1 minus, so my overall charge is +7. On this side, I have a +2 and 0, so my overall charge is a +2. Pick your more negative side, or excuse me, sorry, more positive side, that's your +7, and now you're going to add electrons to balance it out. So how many electrons do I need to go from a +7 to +2? Well, hopefully you got +5 electrons. Okay? Now, so far, how are we doing? Do you remember that Leo goes grr? I'll even write that down. Leo goes grr. That should bring back a few memories. So what is Leo? Oxidation is lose electrons. Notice I have electrons as a product, so I lost it. Reduction is grr. Gain electrons, reduction. Notice how my electrons are on my reactant side, so that should bring back some memories. So now what? It says balance, if necessary, multiply by integers. We're at this point to equalize electron counts. You cannot lose any more electrons than you gain, or you can't gain more electrons than you lose. It has to be an equal number. So I'm going to multiply this whole part by 5 so that my electrons cancel out. So now I'm ready. So I'm going to write 5 Fe2 plus 8H plus Mn04 minus. I'm going to cancel out my electrons, so I'm not going to write those down. Don't forget, I need to multiply by 5. Okay, and now let's go ahead and check. I have 5 irons here. I have 5 irons here. I have 8 hydrogens here. I have 8 hydrogens here. I have 1 manganese, 4 oxygens, 4 oxygens. So my atoms are balanced. What's left now is to make sure that the charges are indeed balanced. So I have 10 times 2 is plus 10. I'm sorry, 5 plus 2. I'll say it one more time. 5 times plus 2, there we go, is plus 10. Plus 8 is 18. Minus 1 is a plus 17 on that side. Here, I have 5 times 3 is 15. Plus 2 is 17. So I have 17 on the product side. So my atoms are balanced and my charges are balanced. So that's how you do that one. Now, notice we also have that one in acid, so I don't have to do anything new. So I'm going to do the next one. Actually, no, you do the next one. Why don't you pause this? You work on it. Remember, this has been a review. All right, you've already done this, bringing back some really fond memories. So pause this and then see how you do. Okay, welcome back. So let's see how you did. This is 0. This is a 2 plus. What happened? That went up. So that's my oxidation. Okay, so I have copper going to copper 2 plus. My coppers are balanced. I don't have any oxygens. I don't have any hydrogens, so now I just have to balance some electrons. I have a 0. I have a 2 plus. I need to add electrons to my more positive side, so I'm going to add 2 electrons here. Okay, now what? Well, I need to do some reduction. Okay, so how do I know that nitrogen indeed was reduced? So let's check this out. What is nitrogen's oxidation number in NO? If oxygen's -2, nitrogen is +2. What about on the other side? Well, NO3 minus, nitrogen plus 3 times -2 equals -1. Nitrogen minus 6 equals -1. Nitrogen equals +5. So nitrogen indeed was reduced. It went from a +5 to a +2. That makes sense. So let's do this. We have NO3 minus making NO. Well, what's the first thing? Nitrogens are balanced. Awesome. Oxygens are not balanced. I have 3 on the reactant side. I have 1 on the product side. So I need to add 2 more waters to get 3 oxygens on both sides. Now what? I need to balance my hydrogens. I need to put 4H plus here. Now, what's my overall charge? On this side, I have no charge. On this side, I have a +4 and a -1 is a +3. So I have to add 3 electrons. Okay, again, does this make sense? Oxidation. Leo lose electrons. Yes, I lost 2 electrons. Goes GR. Gain electrons. Reduction. I gained 3 electrons right over here. There we go. So that does make sense. Now, what's my problem is that my electrons are not balanced. So I'm going to multiply one side by 3, one side by 2, so my electrons are canceled out. So now I'm going to carry my 3 through, so 3 coppers, plus I'm going to carry my 2 through. Well, I'm going to leave out my electrons because they're going to cancel out, so 8 plus 2 NO3 minus yields 3 Cu2 plus 2 NO plus 4 H2O. So how did you do? Let's check this out. Let's check our chart or our balancing. We have 3 coppers, 3 coppers, 8 hydrogens, 8 hydrogens, 2 nitrogens, 2 nitrogens, 6 oxygens. 2 plus 4 is 6 oxygens. Now let's check our charges. All right, so let's see here. We have 3 neutrals plus 8 minus 2 is a plus 6. Here we have 3 plus 2 is plus 6, and neutral, neutral, we are good. The last thing you should do is go back. Is this an acid or a base? I bet you're a happy camper. It is an acid. We are totally done. Well, let's go see what we do when we have a base. Oh, you're going to be so happy with this one. It's identical except for the last step, okay? So let's check this out. I already see the gimme right there. So what did sulfur do? Sulfur went from a -2 to a 0, okay? This elemental sulfur is going to be 0. So that tells me that it went, what? Oxidized or reduction? Hopefully you knew it was oxidized. It went up. Well, what about this S right here? Well, it stayed the same. It didn't change, okay? So it's still -2. What I would do with this manganese 2 sulfide, for this, I would leave out the 2 minus. In a sense, as a spectator ion, because some of this sulfur here did not change to become this sulfur here. So I would just worry about the other one, and we'll deal with it at the end. So here's my reduction. I'm sorry, my oxidation. And now what? So, whoops. Love my board. Here's oxidation. I go from S2 minus to S. My sulfurs are balanced. I have no oxygens. I have no hydrogens. So where do I put my 2 electrons? Hopefully you know I'm going to put them right there. So that's my oxidation. My reduction, we've already done permanganate, so hopefully you know it's a +7. So here's my reduction. I have MnO4 minus going to Mn2 plus. Okay, so now what? Let's see here. My oxygens, I'll put 4 H2Os over here. I will put 8 H pluses over here. And what's my charges? Well, this is a +7 and this is a +2, so I need to add 5 electrons. This looks kind of familiar, doesn't it? So I'm going to multiply this by 5, but I'm going to multiply this by 2. Okay, so if I put us all together, all right, let me erase this so I have a little more room. All right, there we go. So I have 5 S2 minus plus 16 H plus 2 MnO4 minus. I'm going to leave out my 10 electrons, yields 5S plus 2 Mn2 plus 8 waters. Okay, so how did that go for you? Hopefully it went pretty well. If you are uncomfortable with the fact that you left out that sulfur here, now you can stick it in. Okay, so if I have 2 right here, the 2 right here, do you see what I'm pointing to? These 2 manganese or manganese ions, that means I need 2 sulfide ions to make manganese sulfide. So I'm going to put 2 S2 minuses over here. So I need to add 2 S2 minuses over here. So now what do I have? Let's check this out. I have a total of 7 S2 minus plus 16 H plus 2 MnO4 minus makes 5S plus 2 MnS plus 8 H2O. Okay, let's check to make sure I balanced it all right. So here I have 7 sulfurs. Here I have 5 plus 2 more makes 7 sulfurs. 16 hydrogens, 16 hydrogens. 2 manganese, 2 manganese, 8 oxygens, 8 oxygens. Let's check out my charges now. I have 7 times -2 is -14, plus 16 minus 2. Well, what does that all add up to? 0. And what about this side? Neutral, 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 0. Okay. I am not done yet, though. Okay. So what I need to do next is make it in base. Do you remember what I do? Find your H plus. Here it is. It's over here on the left side. It's right here. Actually, I'll circle it in red. Okay, how many H pluses do I have? I have 16. So I'm going to add 16 OH minus to both sides. Do you remember doing this? So now what do I have? I'm going to erase this because I'm running out of room. Maybe you didn't write so large. I have 16 H2Os. Okay, but wait a minute. I have 8 H2Os right here. What can I do with that? I can take out this 8 and subtract from here, and now I have 8 H2Os. So what I would do for my final answer, all right, let's do this again. So I have 7S2 minus plus 8 H2O plus 2 MnO4 minus yields 5S plus 2 MnS, yikes, I'm running out of room, plus 16 OH minus. All right. Okay, so one more time, let's make sure we're all balanced. I didn't lose anything. I have 7 S's, 5 and 2 make 7 S's. Let's see what else. I have 16 hydrogens. I have 16 hydrogens. I have 8 plus 8 is 16 oxygens. I have 16 oxygens. I have 2 manganeses. I have 2 manganeses. Let's check out our charges one more time. I have 14 minuses and 2 more minuses, so it's 16 negatives, and over here I have 16 minuses. So I am convinced I did that right. So why don't you go ahead and do number 4 all by yourself, and I'll tell you what, I'm just going to put the answers up. You can see my work, study my work if you didn't get what I got. All right, so pause this, and next time you hear my voice, the answers will just suddenly pop up. Okay, well, here is my mess. Hopefully we can figure out what I did. I first wrote my 2 half reactions. My reduction is right here. You'll see that I made the hypochlorite go to chloride, and I balanced it off. Then I made my chromium 3 hydroxide ion go to chromate ion, and that was my oxidation. Notice my electrons didn't work out, so I had to multiply the top by 3 and the bottom one by 2. So my first blue line is where I put the whole thing together. Why did I circle the 6H plus on the left and the 8H plus on the right? I can combine those two. So that's what I did in my second blue step. All right, so over here, I don't know if you noticed, but what I circled in red over here, do you see my face? I'm kind of pointing to there. That is where I have 2 hydrogens on the right-hand side. So now what I needed to do is put it in a base solution. So my 2 H pluses as a product, I added 2 hydroxides to both sides. They're in red. Okay. So then I, in my black line, put everything together, and notice what happened. I circled them in green. I have 3 waters and then 2 waters, so in my final blue line I have 5 waters. So as always, what should you do before you're done with the problem is check all your work. Okay, so let's do that right now. So here I have 3 chlorides. Why aren't you working here? I have 3 chlorides, here we go, and 3 chlorides, that works. I have 2 chromiums and 2 chromiums, that works. Oops, I forgot my oxygens. I have 3 oxygens and 8 oxygens make 11, and 2 more make 13. Here I have 5 oxygens and 8 oxygens make 13. That's good. Let's try my hydrogens next. I have 8 hydrogens and 2 more make 10 hydrogens. Here I have 10 hydrogens. Okay, let's check my charges. Here I have a -3. Here I have a -2 and a -2 for a total of -7. I hope that works. Here I have a -3, a 0, and a -4, which gives me a -7. So I know it's a lot of work, but that's how you do it. So why don't you go ahead and do number 5 finally. It's an acid, so it's a little bit easier. Go ahead and do that. And pause this, of course, and then the next time you hear my voice, the answers will just magically appear. All right. Alright, so this one I thought was a lot easier. There are two little tricks that you hopefully didn't forget about. What was our first step? Go back to the front page. You have to balance the elements. So notice what I did here. I started out with just one chloride and one chlorine. So I had to put the two out in front to balance the elements. Had no oxygens, had no hydrogens, so then I had to balance it with two electrons. The same thing here also applied for the chromate or the dichromate and the chromium ion. Here I have two chromiums, so I had to put this two out in front first. Then I balanced my oxygens with water. Then I balanced my hydrogens with H+, and then I counted. So I have 14 hydrogen pluses, so 14 pluses and 2 minuses, so it's a plus 12 on the reactant side. But because of this 2 here, I now have a plus 6 on the product side. So I needed the 6 electrons over here. So I only had to multiply the top number or the top oxidation by 3 to balance out my electrons. So I got 6 chlorides plus 14 H plus 1 dichromate makes 2 chlorine, diatomic elements there, 2 chromium ions and 7 waters. Again, if we wanted to check this, I have 6 chlorines, 6 chlorines. I have 14 hydrogens, 14 hydrogens, 2 chromiums, 2 chromiums, 7 oxygens, 7 oxygens. As far as the charge goes, I have minus 6 plus 14 minus 2, and that equals a plus 6. Over here, I have 0 plus 6 plus 0 for a plus 6. So hopefully that was a good review. So why did we go through all of this? It's because we're going on into what a voltaic cell is, okay? So what is a voltaic cell? Also otherwise known as a galvanic cell, generate electricity from a spontaneous chemical reaction. So this is what the basis of batteries are all about. So we put in two metals that will spontaneously start flowing electrons, from the one that will give it up more readily to the one that will accept it more readily. Think back what this oxidation reduction is. Oxidation is losing electrons. What kind of things will want to lose electrons? Oh, like your group 1s. Lithium would like to lose electrons to become lithium ion. Sodium would like to lose electrons to become a sodium ion. Okay, those are going to be very common oxidations, if you will. The problem is that if you stuck it in water, those could catch on fire. Sir Humphrey Davy tried doing that and lost, maybe his eye or something. I'm not sure. He lost something. But anyway, so this is the idea of how batteries work. Actually, if you want to look it up, you can look up that the Italian physicist Volta was the one that came up with this first battery and really revolutionized chemistry in the fact that now you could isolate these elements by using electricity. So anyway, it's kind of interesting how he did that. But back to what you need to know. So oxidation, we already said, is the loss of electrons and occurs at the anode. So how do I remember this? Ox. Do you like my picture? That's my ox, all right? So ox. And, excuse me. So the substance oxidized is also called the reducing agent. Reduction is the gain of electrons and occurs at the cathode. So what do you notice about my cat? It's red. Red cat. Therefore, I call it my reduction occurs at the cathode. I just make red cat. There we go. Red cat. So it occurs at the cathode. So reduction. It's the substance that is reduced is called the oxidizing agent. So now we have something called redox energy. Heat can be produced, but more important, electricity can be produced if the reactants are separated. You need to separate them so that you can harness that electricity. Okay, so reactants can be separated by a salt bridge. It allows the ions to complete the circuit. Can be separated by a porous partition. Electrons then travel through some wire. So I started this from past time, it looks like. All right, so what is a galvanic cell? It is a device in which the chemical energy is changed into electrical energy. Again, oxidation occurs at the anode, reduction occurs at the cathode. There's something called the cell potential. You will also see that is written as in that cursive E with a little naught. You've seen that naught before. What does that tell you? It is at standard conditions. And don't worry, we will talk later about what happens if it's not in standard conditions. So anyway, the driving force, the electromotive force, if you will, on the electrons, potential is measured in volts. So the problem number one, and this is a fairly common AP-like question. All right, here's a picture, and they want you to describe what is happening in the cell, okay? So describe what is taking place. So let's take a look at this pretty closely here, okay? So the anode is the zinc. What's happening with the zinc? The zinc is going from zinc metal to zinc ion. So these ions are being created. So I'm losing the metal, so my metal mass is decreasing. Oh, that's important. Let's write this down. Zinc mass is decreasing. What's happening to the concentration of my zinc ions? I'm making more and more ions, so the concentration is actually going up. Then what's happening over here? My copper ions are grabbing two electrons, all right, to make copper solid. So the concentration of my copper 2+ is going down. What's happening to the mass of my copper? Copper mass is increasing. How is that occurring? Well, you see what's happening here. I'm over here on my left. This is my anode. So my zinc ions are going out into a solution. But keep this in mind. What does oxidation mean? Lose electrons. So where are these electrons going? This way. This way. Here's my flow of electrons. And so here, electrons are plating out on the copper wire. So now what? Or on the copper metal, excuse me. So what's happening now? This copper 2+ saying, hey, baby, there's a whole bunch of negatives, all right? So the copper 2+ is attracted to these negative electrons that are now on the surface of this metal. So what about this salt bridge? Why do we need a salt bridge? What's happening to the charge in my solution over here, this solution? I'm losing the 2+. The nitrates are still floating around. Nitrate, in a sense, is accumulating, okay? Because if copper 2+ is going down, nitrate's not doing anything. You cannot, in a sense, store negative charges. So what happens? The nitrate goes this direction. You see what I'm doing here? That's the path of the nitrate. The nitrate isn't needed to balance out your coppers in a sense, so it goes over the salt bridge into the zinc beaker over here. Why is that needed? Because remember what's happening. You're making more and more zinc plus ions. You need more and more nitrates to balance that out. So that completes my circuit. So the electrons go this way. Electrons always go from the anode to the cathode. That's your path of your electrons through the wire. Okay, you can have a voltmeter to measure that path of electrons. What happens here? The electrons actually go onto that metal piece, so the copper 2+ is attracted to that, and it plates out. So now you have all this metal being deposited on your original piece of metal. So the nitrates are like forced to leave. I have less and less positive charge, so the nitrates go this direction, going into the beaker where more positive charges are being made, so everything is still neutral. Okay, so we will talk a whole lot more about that later. For right now, I believe that concludes section 18.3. Yes, it does. So don't wait to be great. See you later.